Right, hello and welcome to my third video of STEM education. Now, just to clarify to people who may have come onto this and haven't come across STEM before, STEM stands for science, technology, engineering and mathematics. Um, and it's a dual purpose thing, which is to also increase the awareness of children at school about the subjects that lead on to science, technology, engineering jobs, and how they get used. But it also is to encourage people who are in careers in science, technology, engineering, and mathematics to go into schools and tell the kids about the jobs they do and how what the kids are learning at school applies to the jobs. So I've used this mass balance before just to show how it's a more visual guide for children to learn about adding and subtracting, dividing and multiplying. And I did say in the description to my very first video that what I would do is I would go on to teach how this can learn this can teach people about the physics sides of how this work, as it being a balance. So the obvious thing is that, as I said before, if you put a 5 on the left hand side, then it's got to balance by putting a 5 on the other side. And then you can put different combinations on the other side. So if you have a 3 and a 2 on that side, then it balances, showing that 3 plus 2 equals 5. Now, how does this work mathematically? Well, what you're doing is you're causing one side to move over by applying what's we called in engineering structural mechanics a moment. Now, a moment is a mass, okay? So this is a mass, okay? Then they're all same masses, times a distance. So you may have the same mass, okay? But if you put it at a further distance away, it's going to cause a greater moment and make it unbalanced there. So I've got 5 and 2, so I can balance that by putting 7. Now, it's simplified in this instance by the fact that we have got similar masses. So they're all very much similar masses, and they're at equal spacing. So all we have to worry about is at what spaces we do it and the number of masses we have. In the next section, what I'll do is I'll go onto my pen and paper and describe how as I say, the engineering mechanics works. Right, so what is the theory, the structural mechanics behind how the maths students' balance work? Well, if we just draw the balance there, the straight line, with the support in the middle, what we're saying is that the clockwise moments have to be equal to the anti. If I could write properly and spell properly, it help. The anti-clockwise moments. And that's what we mean by it being in balance. Now, what do we mean by moments, this word? Well, basically, the definition of a moment is, well, I'm going to use the term weight because, no, mass rather, because strictly it's the weight times the distance. But for junior children, they haven't yet done Newton's laws of motions, so they don't know the difference between mass and weight. So we'll just say that a moment is equal to a mass times a distance. So if we have a mass, as we do on that balance, and the mass or the weight of the mass is acting downwards, we have the mass there, m, and we have the distance as being L. And that distance is always at right angles to the direction of the mass or the weight acting downwards. And I just realized that when I was writing down, because I just paused the video, that I can't even spell the clockwise there, so that's clockwise. So if we say we've got the mass on the left and the length's on the left, okay, that's got to be equal to the anti-clockwise. No, that's right, that's it. That's an anti-clockwise moment on the left. And this is going to cause a clockwise moment. So it's a mass on the right times, if I could draw a straight line, times the distance to the right. Okay, so our equation is, we do the clockwise moment first, if we get it the right way around. So it's m r times l r, rb to the right hand side, has got to be equal to the mass on the left hand side times the distance on the left hand side. So that is the theory that is mine, and it's not only just my own, but is the general theory of balancing on a seesaw balance like that. And in the instance of the example I showed with the mass balance, so what we had there was one of these blue weights here, which is a standard weight, so they're all the same weight. So that was acting down at 5, so that's a standard weight we just called m for one mass. And that was balanced by a 2 on the right hand side and a 3, so a mass at the 2 position and then a mass at the 3 position. Okay, so using that equation of the clockwise moments has got to equal the anti-clockwise moments. So what we had there was that 2m plus 3m must equal, so that's 2m there and then 3m there, has got to equal and be opposite to the other single m at the distance of 5, so 5m there. And as with any good equation, we know that we've got the same thing multiplying every part on each side. We can just cancel them out, and lo and behold, we get the sum that 2 plus 3 equals 5, which is just as well, because we certainly don't want 2 plus 3 to be equal to 6. So that's a theory of the mass balance as using moments and structural mechanics.